Okay. We are recording, guys. We're getting on to the actual work for today. Okay. Ring that bell, guys. Ring that bell. Anyway, getting stuck in. So, we're going to look at periodic functions. Now, everyone look at your calculator. Now, back to me. Now, back to your calculators. Now, in your calculator, guys, in your calculator, can you see where it says sine, cos, and tan? Who remembers using sine, cos, and tan? What does sine, cos, and tan have to do with? Wrong! Sine, cos, and tan. Sine, cos, and tan, guys, look like this.
Sorry, David's missed. It's my fault. I'm taking it. You said butthole.
Sine, cos, and tan are functions. Like a cubic, like a quadratic. It's true you can use them to deal with triangles, and I'll explain how we use triangles. But they're basically graphs look like this. That's what sine and cos look like. Tan is a garbage function because it looks like that. Then it goes off to infinity all the time. It sucks. I don't like it. It's a garbage function for garbage people. Oh dear. Okay, so we're going to be studying sine, cosine, and tangent. Please don't call it sin. Sine. I know saying that every year I say it, and then people are like, haha, sin, sir. You got me. But yeah, sine, cosine, and tangent are what they're called. And yeah, I was going to ask you to close it all, but thank you. They are powerful tools that can be used to understand the world around us, from blood flow in a human body through to the motion of a Olympic biker or the movement of the tide. Trigonometric functions can model and help us understand a wide variety of scenarios. Periodic functions also have a huge impact in physics, chemistry, biology, as well as both pure and applied math. There's two types of math, pure and applied. Pure math is where it's like, is 2 an even number? Prove that it is. And it's actually very difficult to prove that 2 is an even number. Wasn't supposed to be. Pure math, it's very interesting, but they do stuff like set theory and number theory. Like, how can you prove that how do you prove that even numbers are even? And can you prove that 1 plus 1 actually equals 2? How do we know that for a fact? And trying to actually show that rigorously so that it is incontrovertible that is true.
Put him in a group with another part.
Oh, you might have a promising career in pure maths ahead of you, Lachlan. So to understand trig functions, we need to... It says revisit. You guys have never looked at radians before, so we're going to learn about radians. Well, that's the other thing. If you look at your calculators, can you press the mode button? Now, on the third or fourth row, it should say like radians, degrees, and it should be on degrees. You just go ahead and flick that over to radians. Oh, there probably is, but I don't know how it works on that one.
You should say press it, because degrees already.
We will be working in radians, yes. Yes. No. The only thing it'll affect is using sine, cos, tan. If you go to use sine, cos, tan, and you want to put in like 30 degrees, and your calculator is in radians, it is going to think you're putting in 30 radians, and is going to give you the wrong answer. It was a running joke when I was in high school, many centuries ago. Whenever someone got a question wrong, people would say, like, "Oh, your calculator must be in radians," because if you don't check in, you got to swap between them as needed. Okay, so we're going to examine then after that derivatives and gradients, and talk about that. So yeah, over here, sine, cos, tan. You can see sine and cos. They're these nice, gentle, curved functions. They just repeat it over and over again. Then you have ADHD tan over here, just going up to infinity and back, just like AKA. Don't make me yell wrong at you again. We're going to spend probably 2 lessons on circles and radians, and then we're going to start really digging into trig functions. And that'll take probably 2 weeks. So that'll probably be the rest of the term, us doing trig functions. Cool. So radians, high level mass. Forget everything you know about degrees. We don't use them anymore. They're useless to you. I mean, until they're not. Until like next term. No, sorry, next year. And then you have to go back to degrees. But for the next term, forget about degrees. This is a really strange definition, guys, but basically, a degree is a measure of separation. So that means if I have 2 things, degrees, the only thing it can measure is how separated 2 things are. A radian, however, is a measure of rotation. So if my pen is, that's done 1 full circuit, 2 full circuits, we need to use radians to measure that. So how they work. A radian measures the angle needed to draw an arc exactly the length of the radius. That's why it's called a radian. So if this is my circle, guys, say my circle has radius 1, the arc in here, the angle in there, theta, that causes the arc length there to also be 1 is 1 radian. How big is the circumference of a circle in compared to the radius? Or compare, so pi, the diameter of that circle is pi times the diameter. Sorry, the circumference of the circle is pi times diameter. Diameter is 2 times the radius. So if each radian gives you 1 measurement, there should be 2 pi in there, so about 6 and a bit. So there are 2 pi radians in a circle. 2 pi radians in a circle. I'm going to say this like 8 million times because we're going to be focusing on this for the next few weeks, but there are 2 pi radians in a circle. So if you look at our diagram down here, if we had an arc length of 2, how many radians is that angle? 2. If I had an arc length of 4, how many radians is the circle? 4. That's all it means. So the radian just ties the radius of the arc, the length of the arc, to the angle that was turned. So that's why we say it's a measure of turn. So we know that a circle has 360 degrees in it. Whoops. 360 degrees. How many radians can you fit in a circle? Well, we need to use our knowledge of a circle's perimeter. 1 radian makes an arc 1 unit long, 2 radians makes 2 units long. Stands to reason that whatever the circumference of the whole circle is, it will take that many radians to fill a circle, same way 360 degrees will. So let's use the circumference rule to identify how many radians in a circle. I've just explained this. How many radians in a circle?
2. Oh, 6.
2 pi. We don't use r because regardless of what the radius is, because if the radius is 1, there's going to be 2 pi radians in the circle. If the radius is 10, there's still going to be 2 pi radians in the circle. The radius is 15, 2 pi radians in the circle. So we know that circumference equals pi times diameter. What's the relationship between diameter and radius? Because we want to relate this back to radius.
Diameter is like halfway.
So diameter to radius, how many radiuses in a diameter? 2. So so there's 2 pi times the radius is the diameter, and we know that the arc length equals the circumference in this case, because we want to go the whole way around, so the arc length will be the whole circle. So know that for a 360 degree circle equals 2 pi radians. Now, you remember, guys, degrees is just like a little circle over it. Radians is a little C over it. Why C? Why not R? I don't know. The person who decided that is dumb. So there are 2 pi radians in a circle. Questions, comments, concerns? Okay, I'm going to throw a curveball at you. I'm going to ask Tyson. If there's 2 pi radians in a circle, how many radians in a semicircle? 1.
Pi radian.
Yeah, pi radians. So there's only pi amount, 3.14 radians in half a circle. How many radians is equivalent to 90 degrees, Kurt? If there's 2 pi radians in a full circle, 1 pi in, half, or pi in 2 radians, half a pi worth of radians. Does that make sense, guys? So in general terms, how many degrees are in pi radians?
180.
180. There's 2 pi in 360. That means pi radians must be 180. Half a pi of radians is 90. A quarter pi radians would be 45. Pi on 3 radians would be 60. So on and so forth. If what I just said, you're like, whoa, that makes no sense, buckle in for the next few weeks. So we're doing tons and tons of fractions that have pi on the top. Oh, yes. So now that we know there's 2 pi radians in a circle, we can figure out how to convert between radians and degrees. Use the fact that there are 2 pi radians and 360 degrees in a circle to create a rule to convert between them. So we know 2 pi radians equals 360 degrees. Now, Sajith, do you want a rule for how many radians or how many degrees? So do you want a rule for what 1 radian is equal to, or do you want a rule for what 1 degree is equal to? 1 degree. So let's do 1 degree first. We know that 360 degrees equals 2 pi radians. So if I wanted to find what 1 degree is worth, I just divide both sides by 360. One degree equals 2 pi over 360 radians. And if you simplify that, that becomes pi over 180 radians. If we then did 1 radian instead, we know 2 pi radians equals 360 degrees. Pi over 180. So I've just cancelled the factor of 2 top and bottom. If I want to know at 1 what 1 radian is worth, how many radians are on the left-hand side of my equation there? 1 degree.
So it's been
Because you got 2 pi on top, and you got 360 on bottom. So I cancel a factor of 2 on top. I cancel a factor of 2 on bottom, which leaves 180 left over. How many? So I've got 2 pi radians equals 360 degrees. How many radians do I have? How many radians equal 360 degrees?
2 pi.
2 pi. So to find what 1 radian is equal to, I would divide by 2 pi.
Does that say 1 degree?
Yep. So 1 degree is pi over 180. 1 radian is 180 divided by pi degrees.
So similar.
Or just opposite. Just opposite. So note, guys, we could put those in your calculator. What number's pi, guys? What pi is equal to, roughly? 3.14. Divide that by 180. That's going to be a very small number, isn't it? 3 divided by 180. So 1 degree is worth like hardly anything of a radian. 1 radian, however, if we were to be roughly estimating it, 180 divided by 3.14 would be about 60, roughly 60. So 1 radian is roughly 60 degrees. Roughly. Okay, so we don't obviously want to use those values though, because we're going to try and use exact values as much as possible. It's fine to leave pi in the equation, as otherwise it's just going to become a decimal nightmare, and we don't like that. Okay, so 1 degree equals pi on 180 radians. We can take them and easily convert it. Sorry? The C means radians. The same way that you put a degree symbol next to how many degrees you have, you put a C next to how many radians you have. Sorry? Is it attached to the pi or the 180? Is that what you said? You could pretend it's in brackets. You could put it above the pi. Doesn't matter. Yes. Okay. I want you guys to calculate the following as radians. Should I help you with the first few? Okay. We know 180 degrees. To turn that into radians, so 180 degrees equals 180. Just multiply it by our conversion factor. We know that 1 degree, to get it as, we know that 1 degree, is pi on 180. So 180 degrees is just 180 degrees times pi on 180 radians. So 180 pi over 180.
Are you applying to the C to both the top and the bottom?
So C, think of C as if we were measuring stuff and we're saying meters. So it's just the measurement. It's to the whole thing. It's not to both, if that makes sense. So the C just means radians. So we have pi on 180 radians. Okay? And that makes sense because I told you before that if there's 2 pi radians in a whole circle, there must be pi radians in half a circle, which is 180 degrees. 180. Now, 270, guys, we're going to expect it to be more or less than 1 pi radians. More, because 270 is more than 180. So would we expect it to be up to 2 pi radians? Well, 2 pi radians would be double 180, which is 360. So we're actually going to be less than 2 pi radians. So we're going to be somewhere between 1 pi and 2 pi radians, which it'll end up being 1.5 or 3 halves is what it'll end up looking like. So 270 degrees equals 270 times pi on 180 radians. So you have 270 pi over 180. Is there a common factor on top and bottom? No.
Oh,
There sure is. There's like 20 of them. Is there a common factor, top and bottom? Amber, what do you reckon? 90. If you divide 270 by 90, what do you get? 3. So we get 3 pi on top. Divide 180 by 90, 2. So you get 3 halves pi. Which makes sense with what we said before. It would be between 1 and 2 pi. What does 3 halves represent as a decimal number again, guys? 3 halves is 1 and a half.
Well.
Or 1.5, yeah. Okay. 185, this one's going to be a pest. 185 degrees is just 185 times pi on 180 radians. So it'd be 185 pi over 180 radians. Those numbers are so close together that it's going to be like the only common factor I can sort of see there is 5. 5 goes into 180. It will go into 50 10 times, 40 8 times. So it goes into 90 18 times. So it goes into 180 36 times. So would that be 37 over 36 pi? Okay. Let's do 450. 450 times pi on 180 radians. 450 over 180 pi radians, Lachlan.
shouldn't that be 37 over 30? C, the 6 looks like a C.
It's 36. 450, 180 common factors.
90.
19.
90.
90, yeah.
Sorry.
90. How many times does 90 go into 450? Yes. 5 pi on 2. Now, you may not believe this, guys. You're going to get very, very good at doing these conversions in your head. Yep. You'll be to the point where you'll see like, I don't know, 5 pi on 4, and you'll be like, okay, that's 225 degrees.
Kind of funny how you seriously doubt yourself.
How I seriously doubt you.
Okay. Wait, no.
I just said you would. I just said you would be doing this. Anyway. Questions before we move on, guys? No. Are you sort of seeing the pattern? Generally, why not actually give you? I'm going to give you one to do on your own. 240 degrees. And I think the answer is 4 pi on 3. No, yes, 4 pi on 3. I think. I mean, I also think I'm right, so hope so.
How come we're doing 80, not 1?
Where's that?
1 by radian.
5. 4 over 3, I think. So you get 240 over 180. They have a common factor of 60. 80. 80 doesn't go into 180. So guys, we should be able to prove there's 2 pi radians in a circle, convert between radians and degrees. Can I get you to have a go at the problems on page 507? 507.